Welcome to this session on rates of reaction. In this session, we will look at the collision theory, factors that influence the rate of reaction, measuring the rate of reaction, reversible reactions, and finally we will end up with some questions. It would be really useful if you are able to take some notes as we go through this, as it will help you with your revision. So firstly, for a reaction to happen, these reactants have to come together and they have to collide with enough energy to form the products. Now, there is a minimum amount of energy that is required for this to happen, and that minimum amount of energy is called the activation energy. The frequency of these collisions determines the rate of reaction. The more frequent these collisions are, the faster the rate of reaction. The less frequent these collisions are, the slower the rate of reaction. So what we're going to do now is we are going to consider the 4 factors that may speed up the rate of reaction. So firstly, let's consider temperature. Some particles at a colder temperature, the particles will not be moving around as quickly as the particles if we heat the substance up. Now, if we're heating the substance up, then that means the particles are gaining energy. And if they're gaining energy, they can move around faster with more energy, which means we will have more successful collisions at a faster rate. So to summarise, increase in temperature means the particles will move faster. If they're moving faster, they will collide more frequently. And also, if they are moving with more energy because they have gained energy because we've increased the temperature, that means that there will be more successful collisions. So an increase in temperature indicates that we would have an increase in rate of reaction. Now let's consider increase in the concentration or pressure of the reactants. If we increase the concentration or pressure of the reactants, then that would mean that there are more particles in the same volume. And if there are more particles in the same volume, that means that there would be less space between the reacting particles. So less space between the reacting particles means that there will be more frequent collisions, therefore increasing the rate of reaction. So to summarise, increase the concentration or pressure means there are more particles in the same volume. This means there is less space between the particles. And this in turn would mean that the collisions are more frequent. Now let's consider the surface area to volume ratio. So if one of your reactants are a solid, then if we break the solid up into smaller pieces, then this would mean that the solid with the smaller pieces has a larger surface area to volume ratio. So if we break the large solid piece up into smaller pieces, that means we've increased the surface area to volume ratio, which means the reacting particles have a larger surface area to work with, therefore the collisions become more frequent. And so if there's more frequent collisions, the rate of reaction is increased. And lastly, a catalyst speeds up a reaction without being changed itself. And the way in which this works is this minimum amount of energy that is required for a reaction to happen with a catalyst is decreased. So the catalyst is providing an alternative path which uses a decreased amount of activation energy from the original. Therefore, the reaction will happen more quickly at a faster pace. So the frequency of collisions increases due to the alternative path requiring a reduced amount of activation energy. So in summary, if we increase the temperature, we increase the rate of reaction due to faster particles moving with more energy, so more successful collisions more frequently. If we increase the concentration, we also increase the rate of reaction, because an increase in concentration or pressure means the particles are closer together, so there's more particles in the same volume, therefore more frequent collisions, therefore a faster rate of reaction. If we break a large solid into smaller pieces, we're increasing the surface to volume ratio, which means the reactants have more of a surface area to react with, so we increase the frequency of collisions, therefore increasing the rate of reaction. And lastly, if we use a catalyst speeds up the rate of reaction by providing an alternative route for the reaction with a lower activation energy. We can work out the speed of a reaction by recording the amount of product that's formed in a reaction or the amount of reactant being used up. Now on the graph, the first part of the graph will be showing us where our reaction is the fastest, and this is where the reactants are coming together very quickly with frequent collisions to form our product. Now as the reaction goes on, our speed of reaction will start to slow down until we are forming no more products, which means the reaction has finished. If we carried out the same experiment but at a lower concentration or a lower temperature, or we had a larger surface area, then the graph would not be as steep, and we would show this by the graph being lower than our initial graph, meaning that in the same amount of time we have less of our products forming. However, we would still have the same final amount of product being formed. Now, to work out the rate of reaction, we would have to work out the amount of product that's formed in a particular time taken. And the way we would do that is, depending on the graph that we are looking at, we would first draw a tangent to the curve. Once we've drawn the tangent to the curve, we would work out the gradient in the same way as we would do in maths, with the difference in y divided by the difference in x. And in this case, the difference in y is the amount of product formed or the reactant used up, divided by the difference in x, which would be the time taken. So if we drew that on our graph, it would look like this. The rate of reaction can be observed either by how quickly reactants are used up or how quickly products are formed. Now, in our first example, we can use a precipitation reaction to observe this. So we would have hydrochloric acid and sodium thiosulfate, which are both clear liquids. We would set up our equipment so we have a piece of paper under our conical flask, so when we look down our conical flask, we're able to see the cross. As soon as we add the two solutions together, we would start our stop clock, and when the reaction starts, because it's precipitation, the solution will start to go cloudy. When we are no longer able to see the cross through the conical flask and through the solution, which is becoming cloudy, we would then stop the stop clock and record our results. We could repeat the experiment either using different concentrations of hydrochloric acid or using different concentrations of sodium thiosulfate. And this would allow us to investigate whether increasing the concentration increases the rate of reaction. And if it does, at a higher concentration, we would no longer be able to see the cross in a shorter amount of time. The second way of measuring the rate of reaction is by using a balance. We could put our reactants into a conical flask and put our conical flask onto a balance. As the two reactants react, if a gas is produced, the gas is released into the atmosphere. We do put a piece of cotton wool at the end of the conical flask, and that's just to prevent any liquid from escaping, because we do not want the mass loss to be due to escaping liquid. The gas is still able to get out from the cotton wool, and what we should see is that if we have a faster rate of reaction, the decrease in the mass on the balance would be much faster. We could record the mass at equal intervals and plot a graph to work out the rate of reaction. And the third way of measuring a rate of reaction is by measuring the volume of gas produced, either by using a syringe or by using the over-the-water method. Now, as the gas is produced, the gas will travel through the syringe and push the syringe out. So at different periods of time, we could measure how much gas is being produced, we could plot a graph, and we could work out the rate of reaction. Now let's consider reversible reactions. When we have a reversible reaction, it is shown by having an equilibrium sign going from the reactants to the products. What this means is that we have a forward reaction occurring at the same rate as a backwards reaction. So overall, we don't see any change in the concentration of reactants and products. For an equilibrium to be reached where we have our forward and our backwards reaction happening at the same rate, the equilibrium has to be in a closed system. So this means that any gases produced are not able to escape into the atmosphere. So let us consider an example. Now let us consider reactions in terms of whether they are endothermic or exothermic. If a reversible reaction is endothermic in one direction, it would always be exothermic in the opposite direction. So let's consider an example. So in this example, if we heat up our blue hydrated copper sulfate crystals, we drive the water off and we end up with white anhydrous copper sulfate crystals. As we are putting heat into the system to turn the hydrated copper sulfates into anhydrous copper sulfate, the forwards reaction is endothermic. Endothermic meaning heat energy is taken in. And if the forwards reaction is endothermic, then the backwards reaction, where the anhydrous copper sulfate are combining with water to produce hydrated copper sulfate, is exothermic. Exothermic meaning heat energy is given out to the surroundings. And in a reversible reaction, if one of the directions of the reversible reaction is endothermic, the opposite direction of the reversible reaction will always be exothermic. Now, in an equilibrium, the equilibrium can lie to the right where the concentration of the products is greater than the concentration of the reactants, or the equilibrium can lie to the left, where the concentration of reactants is greater than the concentration of the products. And the position of the equilibrium will depend on some specific conditions, and these conditions would be the temperature, pressure, and concentration. Now, according to Le Chatelier's principle, we have the idea that if we change the condition of a reversible reaction in equilibrium, the system is going to try and counteract the change that we have made. So let us consider our reaction here. We have nitrogen gas joining with hydrogen gas to produce ammonia. The forwards direction is exothermic, which means it releases heat energy to the surroundings, and the backwards reaction is endothermic, meaning that it takes in heat energy from the surroundings. So let's consider what the impact of a change in temperature would have. So if we decrease the temperature of our equilibrium, then the equilibrium is going to try and shift, so it releases more heat energy to the surroundings to counteract the fact that we have decreased the temperature. So in that instance, the equilibrium will shift towards the right. If we increase the temperature of the system, then the equilibrium will shift in the direction where it takes in the extra heat energy that we are putting into the system to counteract the change, and that would be in the endothermic direction. Now, still using the Le Chatelier's principle, let's consider the impact that change of pressure would have on our reaction. So if we increase the pressure, the equilibrium tries to reduce the pressure that we have increased, and it does this by moving in the direction where there are fewer molecules of gas. So if we consider this particular reaction, we have 1 mole of gas here, we have 3 moles of gas here, and we are producing 2 moles of gas on our product side. So altogether on our reactant side we have 4 moles of a gas, and on our product side we have 2 moles of a gas. So if we are going to increase the pressure, so by increasing the pressure we're trying to push the particles closer together, the equilibrium is going to try and reduce this by moving in the direction where there are fewer gas particles. So in this case, the equilibrium will shift in the forwards direction. If we decrease the pressure, then the equilibrium is going to shift in the direction where there are more molecules of gas. So in this instance, a decrease in pressure will shift the equilibrium towards the left. So lastly, let's consider the impact of concentration according to Le Chatelier's principle on our equilibrium here. So if we increase the amount of reactants we have, then the equilibrium is going to shift in the direction to reduce the amount of reacting particles we have, which would be to produce more of our products. However, if we decrease the amount of reactants we had, then the equilibrium will try and counteract that by having the backwards reaction a shift occurring, which means more of our products would be changing into our reactants. So according to Le Chatelier's principle, the equilibrium will always shift in the way to counteract what we do. In this first question, we can see that we have a graph of a reaction occurring that produces a gas, And the question is, use the graph to describe the changes in the rate of reaction from 0 to 35 seconds. So at the first part, we can see that the gradient is quite steep, so the reaction is occurring quite quickly here. So at part 1, we say the reaction is fast. Then, after a little while, the gradient is becoming less steep as the reactants are being used up, so the reaction is starting to slow down. And then lastly, at part 3, the graph is leveling off, which means no more gas is being produced, so the reaction has stopped. Now you can see on the graph I have numbered positions 1, 2 and 3 just to make it absolutely clear which parts I am talking about. Then the next question says, what was the total volume of the oxygen gas collected? So where the graph has levelled off, if we read off where the volume is, that shows us that we had 21 centimetres cubed at the end. Now in this next question, we have an investigation where someone has put 50 centimetres cubed of sodium thiosulfate into a conical flask. They've heated the sodium thiosulfate solution to a particular temperature. They put the flask on a cross drawn on a piece of paper, added 5 centimetres of hydrochloric acid and started the stop clock. They've stopped the stop clock when the cross can no longer be seen and repeated the experiment at different temperatures. And we have our equation showing us what our reactants and our products are. And the first question is, which product is a gas? So after the arrow, we're looking at all of our products and we're looking for the one that has a G after it for gas, and that would be our sulfur dioxide. Then on our graph, we've drawn our line of best fit and we've left out our anomalous result. And the first question on the other side after the graph is give a possible reason for the anomalous result, and that could just be that we've just completely missed when the cross has disappeared. Now for the next question, we have the reaction at 20 degrees Celsius produced 0.32 grams of sulfur in 64 seconds. Calculate the rate of reaction at 20 degrees using the equation. So it tells us the rate of reaction is the mass of the sulfur, which was 0.32 grams, divided by the time taken, which was 64 seconds. And if we calculate that out, it would give us an answer of 0.05. Oh, sorry, that's wrong. 0.05 grams per second. And then for the next part, it says give 2 reasons why the rate of reaction increases as the temperature increases. So we have to tick 2 boxes. So it says the particles move faster. Well, if you increase the temperature, yes, the particles will move faster. The particles collide less often. That's not true. All the particles have the same amount of energy. That's not true. And the particles collide with more energy. Well, yes, that would be true. And the number of particles increase. That's not true. And then for the next part, out of the words given, we have to choose the right word to put into the sentence. The minimum amount of energy particles must have to react is called and that should be activation energy. So now we have an investigation where we're heating copper carbonate and we're bubbling any gas being produced through lime water. So it says the student used the changes to the lime water to measure how long it took for the carbon dioxide to be produced, and describe how we would do this. So here we would measure the time taken from when we start heating the copper carbonate to when the lime water has fully become cloudy. Now The observations have been written down at 3 separate time intervals, and we need to explain what's happening at each time interval. So for the first part, it says suggest the reasons for observations between 0 and 1 minute. So between 0 and 1 minute we have a slow release of gas bubbles, but the lime water does not change. The solid in the test tube was green. So the explanation there is to start with, the copper carbonate is not decomposing, which means it's just air going through the lime water, and that will not make the lime water cloudy. Then for the second time interval, we have a fast release of gas bubbles and the lime water changed at 1 minute and 10 seconds. So here the copper carbonate has started to decompose, which means carbon dioxide is being produced, making the lime water go cloudy. And that then at our third time interval, we've got no release of gas bubbles. The solid in the test tube was black, and that's because the solid in the test tube is the copper oxide, and so all the copper carbonate has already decomposed, therefore no carbon dioxide is being produced.